Okay, Assalamualaikum warahmatullahi wabarakatuh, and a very good day to everyone. Okay, in this session, we will continue the final topic. We will continue on the final topic on the chapter 3 related to the valve, in which we're going to further understand about the issues related to the valve. Okay, we have learned some characteristic before, some we have learned before in the previous topic about some calculation related to the characteristic. We have understand about general configuration of uh, the valve, and then now we come to the issues or problem related to the valve. Okay, there are two very popular issues, very popular phenomena related to the valve that will trigger a damage or failure of the valve, known as flashing, and the other phenomena known as cavitations. Right. These two phenomena, okay, flashing and cavitation only occurred in the pipeline when the fluid, okay, the fluid following through a small opening here, like this one. When, in other words, this flashing and cavitation occurred in the pipeline whenever it passing through a valve. Why a valve? Because there will be a small opening here to allow the liquid flow. And whenever we have a constriction or obstacle or obstruction in the pipeline, just like this one, there will be a pressure drop, as what we've learned before in the previous topic. There will be a pressure drop. For example, if the flow in pressure is 10 psi, and the outlet pressure definitely will not reach to the 10. Probably it'll drop to 9, 8, etc. It depend on the specification given. Okay, in this case, whenever we have a pressure drop between in and out, so there will be a problem and issues in which it will trigger a flashing. Okay, a flashing known as flashing. Okay, what is flashing? Okay, later we will check later what the detail. Before I come to this definition, flashing and cavitation. Okay, let first understand this diagram, this good representation. Okay, so we have the general configuration of valve pipeline and valve like this. Okay, and if we translate into the flow of fluid together with the plot of pressure, okay, we're going to have this kind of plot. So we have flow in, and then water will be compressed, will be forced through the small opening here. In this case, it is a valve, a gate, no matter what type of the valve is. So there will be a pressure drop at this point, and the bottom one will be just after uh, the the small opening here, about this point. Okay, so we will reach to the minimum, and then this pressure will regain, and it probably it will regain up to a maximum value. Okay, P2. Okay, pressure 2, the highest, the high, and this is can be the lowest possible, which is P2, low. So we will have either high or low, and it will never reach to this level, to the original level of P1. All right. So we have here. So if we fully understand this, a pressure, say 10 psi, and it drop to 7, 9, 5, etc. And this one further down, down to 3, and then it will recover to a certain level, say 9 and 7, in which we classify as the highest possible and the lowest possible. All right. This is something that you really need to know and understand. If we advise you to redraw this one, you should be able to redraw a representation plot of pressure difference after passing through a valve. This is the representation. If been asked in the exam, this is the plot of pressure after passing through a valve. All right, to further understand later in detail, we will see this animation later that will further describe about the flashing and cavitation phenomena. And we also have a pressure plot versus distance through the valve. Okay, in this case, what is pressure? Pressure, of course, the pressure within the pipeline. And what is distance through the valve? Okay, distance to the valve is from A to B. Okay, and of course in the middle will be about a valve. Okay, so if this is 0 centimeter and this one is 10 centimeter, this one probably about 5. So what will have a 5 here, something here 5. So this is 0, this is 5, this is 10. Then about at this point. Okay, so come back to this one, the definition, of course you can read at your convenience. So what is a vapor pressure? Okay, so first we need to know and understand what is the vapor pressure. Vapor pressure of a fluid. Okay, vapor pressure of a fluid is the pressure at which liquid will begin the thermodynamic process of changing from vapor to from liquid to vapor. Okay, it changing from liquid to vapor. Vapor in this case is actually the formation of air bubble. Okay, initially it was a fully fluid, and now it's start to make the air bubble. That is what we classify as vapor. So if we look at this plot, this one you have to fully understand why. Okay, initially, okay, we have a pressure here. Initially, the inlet pressure is high, for example, 10 psi. So it dropped, approaching to the gate, approaching to this the valve opening. So it start to drop to a lowest level around at this point. Okay, at this point, okay, lowest level, and then it will start to regain its pressure toward the downline. Okay, this is upstream, this is downstream. So the liquid will lose the pressure somewhere around the gate area, and then it will recover back at this point, but it will never reach to the original inlet pressure. Okay, so we have 4 category here. Okay, 4 category that you need to fully understand. First, you have to understand, draw a line of vapor pressure. So first, there will be a vapor pressure. First, when we decide if we identify the vapor pressure, so there will be 3 conditions at which the fluid will flow at the downstream here. First, we classify as normal flow. The second is a cavitation flow. And the third one is the flashing flow. Okay. So what the difference between all this? Okay, the normal flow happen when the pressure drop and it never go exceeding the vapor pressure. It never go down beyond the vapor pressure. And then with this in mind, so hopefully the flashing and cavitation will not happen, and it regain its pressure that will make the what we call it as it regain its pressure, and we call it normal because the minimum, okay, the pressure loss or the minimum point of the pressure loss never exceed the vapor pressure. In this case, there will be no flashing. There will be no flashing, and there will be no cavitations. Okay. Okay, there are also scenario in which the pressure drop down beyond the vapor pressure. In this case, this point. Okay, at this point, it start to go down beyond the vapor pressure, and one is regain is pressure, increase a bit, but it increase above, okay, above the vapor pressure, so it will become a fluid. So in this scenario, this one is the formation of flashing, and this one is it become the air bubbles within the liquid will become a fluid, implode. The air bubble implode and it become a all fluid. This is what we call it cavitation flow. Okay, and for this one, okay, flashing flow, flashing, it go down and down beyond, okay, beyond the vapor line, but it didn't recover, or it never regained the pressure loss. So this is the phenomena that we call it as a flashing. Okay, flashing. Okay, flashing is the phenomena in which the air bubbles, the liquid will become passing through the valve, and it will, due to the pressure difference, huge pressure difference, it will form a bubbles. Okay, vapor bubbles. And cavitation is the phenomena in which after the formation of air bubbles along the pipeline at a certain distance, the pipeline will recover, the pressure will increase, and then with the increase of the pressure, the air bubble will implode, and then this is what we call as cavitation. Okay, so don't worry, we'll come to this simple and interesting animation that will help you to further understand the flashing and cavitation phenomena in the valve. Okay, let's watch this video, short video. Let me increase the volume, I'm afraid. Okay. All right, let's watch this video. All right, that is a very simple and interesting animation. Okay, so we have a pipeline here. We have upstream, downstream. We have inlet, outlet, crossing a small gate here, and what you can see, whenever they pass, because of pressure difference, as I explained, pressure 1 is higher to pressure 2 outlet, so there will be a loss of pressure here, and it will cause a bubbles. The formation of vapor bubbles here, this is what we call flashing. This is the flashing phenomena, the formation of air bubbles within the pipeline after passing through a small opening at the valve area. Okay, what happened next after it formed the air bubble? Of course, this is the region at which the pressure loss, the greatest pressure loss, and then along the line here, okay, along the line it will recover, and the pressure will gradually increase. Okay, whenever it increase, so if you can see here along the line, so there will be a increased pressure at this point. And what happened when the pressure increase, you for a simplicity, you can imagine you have a balloon. Okay, you have a balloon, assume this is a balloon. If you have a balloon and you compress it by your hand, or maybe your face around very close to the balloon, at some point, if you increase the pressure, and then the balloon will implode home. Okay, the balloon will implode, pop, and then the impact from the balloon, from the rubber, okay, it will exert a force to your hand. You feel hurt on your hand, and as well as your face if the balloon close to you. Okay, the similar happen to this point. You just imagine this one is a hand. Okay, the pipeline is a hand and your face. So this force will exert to the wall, and that will cause a problem to the wall. I have another video that will further explain how it caused the damage to the wall. The balloon smash your face, okay, explode to your face, and then you will feel hurt. Okay, if if we have a constant implode of this balloon to your face, of course your face will become red, and at some point it will become hurt and bleeding. Okay, the same goes to this pipeline. If the implosions of small air bubble occurred consistently at a long time with a high force, of course, this will cause a severe deteriorations at the pipeline. Okay, if you can see here, okay, so this one, like this one mentioned, so at early stage of this one, you will see a cracking at the pipeline, okay, and of course a noise. But at the severe, you will hear it as a sizzling effect or hissing sound around the pipeline, around the valve area. That is the indication of flashing and cavitations, right? So we have another video here. Let's watch, or maybe I'll just skip where possible. Sorry. Okay, we have another video. Okay, if you can see here, the definition cavitation occurred mainly when the static pressure becomes smaller than the liquid's vapor pressure. Okay, for information, all liquids will have their own respective vapor pressure values. Okay, depending on the type of the fluid, they will have a vapor pressure. So whenever the pressure, the static pressure go smaller than the liquid vapor pressure, it will cavitate. That means that it will have a cavitation. Okay, and this is not important in our case, and probably this is example of the pressure in the boat engine, and then they also cause the vapor pressure. Okay, a good example is piping system through which narrow pipe section pump. Okay, kalau kita if we check this one, okay, this is static pressure. Okay, so this is the formation of cavitation. Okay, this is the illustration how the cavitation bubbles collapse during the in the slow motion view. So you can really see, okay, see, that is what happening. So, okay, look carefully here. Implosion. Okay, this is the real issue. A bubble size and it implode, microjet. Okay, okay, these are some images. Okay, in summary, okay, cavitation bubbles will cause two major issues, which is one is noise, and the second one erosions of the materials. Okay, so valve issues. Uh, Later we will see. Okay, valve issues as what we understand about the flashing and cavitation. So these are some primary factor in the cavitation damage. Okay, first we need to know that the cavitation damage is primarily depending on the cavitation intensity, the pressure difference between the inlet and outlet before and after the valve. If the pressure difference is so huge, and then the intensity will be high, the microjet implosion from the air bubble will severely damage the wall. And the material use, of course, if we are using a stainless steel material compared to the copper, compared to other material, they will have a different strength and capability, in which that also will affect the damage on the cavitation. The length of exposure. For example, we have a small opening and wide opening at long time, at a few months, a few hours compared to the few months. Of course, that one also will be difference. And then we have a valve size, bigger or smaller, the design of the valve trim, and the leakage during the valve is closed. Okay, when you close the valve, sometimes there is a leakage, a small opening that also trigger the cavitation damage. Okay, this video, I think you can watch at this video. Okay, this video will further explain, or with the interesting animations, help you to further understand the cavitation and flashing. I hope you can watch this, and it summarize also the impact of the impact of primary factor of cavitation damage. So if I go through this one very quickly, you will see demo. Okay, so we have a cavitation. Okay, you can watch at your end. So they explain the explanation flashing and cavitations, and then how is happening and how it could affect and how it could cause a damage to the wall. And they also provide some explanation approach that been used, the recent technology that been used to overcome the issues of cavitation and flashing and cavitation. These are some technology that been used to overcome. They invent like this one. They invent that this multiple openings here, multiple hole design to minimize the pressure. So you can read, you can have a look at this video at your end. Okay, we understand about the cavitation. We understand about flashing, how it's happened. So it's happened purely because of the pressure difference. A quick recap, pressure difference between the before and after the opening, after the valve. Okay, so there are some numerical calculations here in which we want to know of the point or actual pressure difference between across the valve. Okay, actual pressure difference, delta P, P1 minus P2. And we want to know the other parameter in which allowable pressure difference. Okay, we remark as, denote as delta PA. A stand for allowable. Okay, and Km is valve coefficients. And we have P1 and RCPV. What is PV? PV is actually pressure vapor. Okay, vapor pressure, PV, P pressure, V vapor. What is RC? Critical pressure ratio, RC. So we have the formula, and then in order for the valve to either, we want to know whether the valve will cavitate or not, we need to know that if the allowable pressure is lower than the actual pressure, the valve will cavitate. Means that a simple analogy, we design a valve to have a certain allowable area. Unfortunately, the actual one is higher than that one, so this valve cannot sustain. And then what we would expect is actually the valve will cavitate. These are the scenario that we need to decide. Okay, so the allowable pressure difference is delta P, as I said. Okay, can be simplified into this. Km, valve coefficient, P1, and PVC. We can call it PVC. PVC is equal to PV times RC. RC is critical pressure ratio. So we can say that PVC is equal to RC times PV, vein contraction pressure. Okay. So in the equations or in the parameter, we name it as vein contraction pressure. PVC, vein contraction pressure. Okay, so we have a simple example here. A control valve is operated under the following condition. Okay, the inlet valve is 40 psi and the outlet is 15. Of course, 40 become 15. This is so-called quite a huge difference. And we have the valve recovery. What is valve recovery? Is actually Km. Okay, Km is equal to 0.5. vapor pressure of the following liquid is 0.5, 0.7, sorry. What is 0.7? Is PV, vapor pressure. Okay, vapor pressure. And vein contraction pressure. Okay, V, what is vein contraction pressure? Vein contraction pressure is actually PVC. Okay, PV, vein, C, contraction. So vein contraction pressure is 0.665. Okay, we have the scenario here. So what we have to decide is actually determine the allowable differential pressure across the vein. So what we have to do, determine allowable differential pressure. So what is the formula? Very simple. This is the allowable pressure difference. So Km times P1 minus PVC. So we've got all of these values. Simply plug in, and then we can we should be able to obtain the value of allowable pressure. So okay, as I said, okay, we know the Km 0.5. We know the P1 is 40. Okay, and we know the we know the so what is okay, we know the PVC. Okay, sorry, PVC is equal to vein contraction pressure PVC. So it is given as 0.0665 0.665 psi. So plug it here, and then we will have a value. Allowable pressure, uh, allowable differential pressure is equal to 19.7 psi. Okay, what is the values here? Allowable differential pressure. Okay, now how about how we going to determine whether this one will cavitate or not? Okay, so we have to calculate, see, and analyze whether the valve will cavitate under this service condition. So we have to know the actual, because why we need to count for the actual? Because the valve will cavitate if, okay, if allowable pressure is lower than the actual pressure, differential pressure. Okay, so we need to calculate for the actual. What is the actual? Actual is delta P, P1 minus P2 is equal to 40 is 1, 2 is, P2 is 15. So the actual pressure is 25. Okay, as we know, if the allowable pressure is smaller, lower than the actual, and then the valve will cavitate. Sorry, okay, the valve will cavitate, means that we put the actual pressure much greater than allowable strength, then of course we will destroy the valve. That is the idea. So the valve will cavitate. How we going to avoid the valve from cavitate? So we need to obtain the actual. First we need to reduce the actual differential pressure lower than the allowable. So in this case, then only the cavitation will not occur. Okay, continue from that one. If the actual pressure is maintained at 25 psi, if we look here, if it is maintained 25, okay, determine the inlet pressure so that the valve will not cavitate. Okay, so we have to understand, in order to make sure the valve is not cavitate, the so the actual has to be lower than the allowable. Allowable is higher, actual one is lower than that. Then the valve will not cavitate. So how we formulate? How we going to calculate? Simple. Okay, simple, because what? We already have the formula here, allowable pressure, and we've got the values here. So the allowable should be 25. Okay, minimum or greater than 25, because the actual is, okay, the actual one is 25. So the allowable should be higher. so that the allowable should be higher so that it will not cavitate. So that's why we set this one allowable to be 25 minimum. Okay, if we calculate that one to be 25, so the inlet pressure need to be increased up to 50, and we solve this algebraic equation that will give you Pi equal to 50.66. Okay, what is 50.66? This is the minimum inlet pressure. Okay, so we need to inject in order to maintain the valve so that it will not cavitate. The inlet pressure, the incoming pressure must be more than 50.66. I can say 51 if you want. That is the minimum. So what you can do? You need to apply more pressure, incoming pressure to the inlet so that, okay, the value will be increased from, okay, from 40 psi to become 51 psi to avoid cavitations. So these are the simple calculation related to the cavitations. So more or less the question final exam will be pretty much similar to this. And then the last topic, okay, the last topic for this one, I think the second last or last topic. So about the valve sizing, okay. The valve sizing, of course, why we need to determine the right valve sizing to avoid the issues uh, in which we want to avoid the flashing and cavitation. We want to use the right valve equipment and all that. Okay, so the formula is very simple. If you can see here, CV is valve sizing coefficients. So we have a chart here. So if the valve sizing is about quarter inch, okay, one fourth, okay, one fourth, the valve sizing coefficient of valve is actually 0.3. And if the valve size is about half inch and then is 3, this is a standard table. And if it is 1, is equal to 14 and etc. So we have the formula here. Okay, so we have Q equal to CV. Okay, CV is coefficient of valve times square root of delta P, pressure difference, divided by G, specific gravity. Okay, so this is the formula. Okay, so this is a simplified example. Okay, find the valve flow coefficient. What if valve flow coefficient is CV, coefficient for a value that must allowed, okay, allowed 150 gallon of ethanol, 150 gallon of ethanol per minute, okay, gallon per minute with the specific gravity 0.8. All right, specific gravity 0.8 at maximum pressure of 50. Okay, maximum pressure of 50. And the required valve size. Okay, let's perform there are two questions here. First, we need to determine the valve flow coefficient. Okay, valve flow coefficient is Q. Okay, valve flow coefficient is Q. This one. And then we use the second one, we need to determine the valve size. Okay, first, we need to find the correct sizing form factor. Valve coefficients, flow coefficient is Q. Valve flow coefficient is equal to okay, sorry, this sorry, not Q. Q is the flow. Q is the flow. Sorry. Valve flow coefficient is CV. Okay, sorry, I got confused. Okay, so we rearrange the formula. This is the valve flow coefficient, CV, and we rearrange this quadratic equation, and that will give you, we know the values of, what is this? Q, we know the Q, okay? Q is flow, gallon per minute, okay? So gallon per minute, the flow rate. And then we have the specific gravity, SG, specific gravity 0.8. And we also have the pressure. Maximum pressure is 50 psi. Why 50 psi is equivalent to 50 pound per inch inch squared cross section area. So pound pressure over inch squared. Okay, that will give you CV. CV coefficient of valve, that will give around 18.97. Right. So we know. Okay, now we know we have valve flow coefficient 18.97. Q is the flow. Flow, what is the flow? 150 gallon per minute. Okay, so we perform these calculations, and then that will give you, okay, mind the equations here, the units here, gallon per minute, and then for us to identify the required valve size is actually 1.5 diameter. Okay, so have a look at here. Okay, sorry. Okay, so we have okay, now we have CV equal to 18.97. Referring to this chart, we have 0.3 CV, this one CV 0.3, 3, 14, 35. So we have 14, 35. So 19, okay, 18.97, 19. 18.97 lie between 14 and 35. So definitely we need to choose the one that is larger. So we choose 1.5 inch valve size. So that has to be, so the next one we're going to use is 1.5 inch or 3.8 centimeter. That is how you're going to decide whether to choose 1 inch or 1.5, 2 versus 3. So you need to choose any values based on CV, valve coefficients here. If the values lie between two values, so we need to choose the larger one. Means that if the CV is 90, so we need to use 3. So because this one is 108, 90 is below 1.8. So that is how you going to choose the valve size. Okay, based on this example, that's why from 1.5 inch or 3.8 centimeter is selected from the table 1. This is table 1 based on the value that we calculate here. All right, very simple calculations here solve to determine the valve sizing. And 3.5, section 3.5, step in selecting a control valve. Okay, how are we going to select the control valve? Okay, how are we going to select the control valve? First, of course, there'll be a guideline procedure, and then in this case, we normally will refer to the handbook, control valve handbook, 5th edition Emerson automation solution. So this is handbook, something that been established that we can actually follow. Okay, first we need to determine, okay, valve selection process, we need to determine the service condition. What is pressure 1, delta P, Q flow, Q is flow rate, T1, temperature, fluid properties, and all that. We need to know the service condition. What is the fluid type? Whether it is water, it is a oil, it is a crude oil, it is a chemical, and all that. We need to identify those. Then we need to calculate the preliminary CV. Okay, we need to determine the valve coefficients. Okay, to avoid cavitations and flashing. So we perform the calculation, and we should be able to determine for the valve coefficient. Then we need to select the trim type. What type of the valve, ball type, the trim type, what kind of things that we need to use. And then next we need to use the valve body and trim type. It depends to the groups. And then we need to choose for the material, whether we want to go for the brass, copper, aluminium, stainless steel, iron, and many other. And then finally we need to consider the operation, whether it is safety valve, open, shut down, shut off, like chemical reaction and all that. So this is the basic of how we're going to decide what type of valve to be used in applications. You don't need to memorize it. It just a matter you need to understand how it's work. Okay. Determine the service condition, calculate the coefficient of valve, select trim type, and then valve body, and then select the materials, and final consideration other aspect, whether that valve need to be used for safety purpose or for emergency, for shut off, for equal percentage, these kind of things. All right, and finally the valve installation after we decide everything. Okay, this is the last one. I think we need to follow the proper installation technique. Okay, be sure the pipeline is clean, inspect the control valve, use a pipeline practice, proper tightening, will avoid uneven gasket and all that. This is something that you can refer to the manuals. So we need to adopt a good practice so that our pipeline will be last longer. Okay, that's about it, about some valve issues. Okay, as we can see here, flashing and cavitations, and then how to avoid that. We need to do a simple calculations to decide for, what? A valve coefficient. Okay, and then allowed us to use the right sizing of the valve, and then we calculate, and then we need to decide and what are the criteria to select the valve, and finally installations. Installation, how to install it. We need to do nicely, uh, install in the right way, like be sure the pipeline is clean. We inspect whether we've got the right valve. This is something that you can actually plan or follow the guideline. These are some references. If you guys, you can see some measurement. 1, 2, 3. The one that we normally refer is Curtis. So you may refer to this one. All right, that's about it. Thank you very much for this time, and hope you can fully understand. For any questions, of course, you can always see me in the class and WhatsApp me. So hope you understand. And should you have any queries, to need a further clarification on this matter, feel free to reach me. And for this section, there are a couple of take a note about this calculations part. Very, very important. Some of them may be included in your test, and some may be in the final exam. All right. Okay. Other than that, it'll be okay. This one also very important. Cavitate or not cavitate condition in which the flashing phenomena, cavitate phenomena for the chosen valve characteristic. All right, with that, thank you very much, and see you in the next section, next video, inshallah. Okay, Assalamualaikum warahmatullahi wabarakatuh.